Hello everyone. While we are on Banach spaces, we have a major advantage of checking whether a function is continuous or not. So that advantage is given by these two theorems. One is the closed graph theorem, which says that if x and y are Banach spaces and f is a map from x to y which is closed and linear, then f is continuous. Open mapping theorem says that if x and y are Banach spaces and f is a function, linear function which is closed and surjective, then f is open and continuous. So we have these two theorems to check whether a function is continuous or not. But what if x and y are not Banach spaces, or what if one of those x and y are not Banach space? Then in that case, we have some examples to say that these closed graph theorem and open mapping theorem is not valid. So in this video, we are going to see those examples where open mapping theorem and closed graph theorem are not valid. Okay, for the first example, I am considering x equal to y equal to c naught naught, which is the space of all convergent sequences with zeros in finitely many indices. Okay, sorry, zeros in all the places except for finitely many indices. Okay, like 1, 0, 0, 0. That is an element in C naught naught. Okay, there we consider the norm infinity. Norm infinity is something that supremum of modulus of norm infinity's definition is norm of xn of infinity equals supremum of modulus of xn of j, where j is equal to 1, 2, etc. Okay, in that case C naught naught is not a Banach space. Okay, now I took a space which is not a Banach space and I am gonna check whether the closed graph theorem and open mapping theorem works or not. For that, x equals x of 1, x of 2, etc. in x, let I am defining the map f to be f of x of j equal to j into x of j, where j varies from 1 to etc. Now I am gonna prove that this map is linear and this map is closed, but it is not continuous, because I am gonna check whether the closed graph theorem works or not. Okay, so f of alpha x plus y equals f of alpha x plus y of 1, alpha x plus y of 2, etc. Then I am applying the definition of the map so that I will get 2 into alpha x plus y of 2, and here I will get 3 into alpha x plus y of 3, etc. Okay, so I am separating it coordinate wise so that I will get f is a linear map. I am not explaining it in detail. If you want to just check the notes. Thus we proved that f is linear from x to y. Now we are gonna assert that f is closed. We know the definition of closed map, right? For a map to be closed, we have to take a sequence xn converges to x in x and f of xn converges to some y in y. Then I have to prove that y equal to f of x. If I proved that, then I'm sure that map f is a closed map. So for proving that, for fixed j is equal to 1, 2, etc. Okay, first of all I am considering the sequence xn converges to x in x and f of xn converges to y in y. I am gonna prove that y equal to f of x. Okay, I know a result that for fixed j is equal to 1, 2 in L power p space, that is the set of all sequence space, xn converges to x in x implies xn of j converges to x of j. So with the help of that result, I am saying that xn of j is converging to x of j as n tends to infinity. Also, f of xn of j is converging to y of j. Now, and also I know that f of xn of j equals j into xn of j. This is by the definition of the map f, and also this also converges coordinate wise. So j into x of j, it converges to j into x of j. Thus y of j equals j into x of j. Why? Because the limit is always unique. F of x n of j cannot converge to two different limits. So they must be equal. Y of j equal to j into x of j for all j is equal to 1, 2. This implies, this is true for all j is equal to 1, 2. This implies y equals f of x. Hence we proved that the map f is closed. Now I am going to check whether the closed graph theorem works or not. That is, I am going to check the continuity of this map. This map is not continuous for sure, because I am going to prove that it is not continuous. If we let xn equals 0, 0, 0, 1, 0, 0, that where 1 occurs only in the nth entry, then norm of xn of infinity equals supremum of modulus of xn of j, where j varies from 1 to etc., is equals 1. Why? Because here the biggest value is 1. So least upper bound should be equal to 1. Also I can say that each and every term in the sequence is less than or equal to 1. So supremum is 1. Norm of f of xn of infinity is what? If I apply the definition of f to this xn, I'll get 0, 0, 0, etc. For this coordinate I will be getting n into x of n is 1. So n 0, 0, etc. So applying the norm to this quantity, what I will get is n. As n tends to infinity, norm of f of xn of infinity converges to infinity, right? Because n tends to infinity. But norm of xn of infinity converges to 1. So I can very well say that f is not continuous, because a map is continuous only when xn converges to whenever xn converges to x, f of xn should converge to f of x, but here that is not happening. So I can very well say that f is not continuous. In the next video, I am going to check whether the open mapping theorem works or not. Okay.